The topic of this video is calculating the isoelectric points of amino acids, and at a more large perspective, this tool can be used to calculate the isoelectric points of peptides and polypeptides. If we remember from our discussions in class, there are 20 essential amino acids, and even though they all have different names and different structures, they have 4 similar characteristics that allow us to characterize them. So these are, to start, our amine group over here on the left. So this general amino acid structure here is drawn as if it is in a solution at pH of 7. So our amine group over here is in a quaternary state and has a positive 1 charge. On the right, our carboxylic acid group. So at a pH of 7, this guy is going to be dissociated, so he's donated his proton, and currently he has a negative 1 charge. Our alpha carbon, which is the carbon directly adjacent to our carbonyl group, and our alpha carbon hydrogen here. And then what makes each amino acid unique from each other, which gives them their unique function and structure and unique characteristics of how they interact with each other, is their R group. So if we look over here to our table from our textbook, we can see that, for example, glycine here, the R group on glycine is just 1 hydrogen, whereas the R group on phenylalanine over here is a phenyl or benzyl ring. And then down here, if we look at serine, we can see that there is a unique methanol attached group here, or just an alcohol attached to a single carbon. And then over here on asparagine, we have an amide that's attached as our R group. And then down here in our bottom left, we have a carboxylic acid group attached for aspartate. And each of these, again, is unique for each amino acid, and it gives them their unique structure, function, and behavior in different solvents, and different solvents that have different pHs. So, taking a little closer look at our general amino acid structure here, over here now we have glycine. So again, I mentioned glycine's unique R group is just 1 hydrogen, so it's basically the most simple amino acid we can look at. So we're going to use it as our example. And now here, I've basically drawn my own version because I'm going to perform some manipulations here. So if you remember from the previous slide, one of the functional groups on our amino acids, again here glycine, is the quaternary amine. So at a pH of 7, this guy is protonated and carries a positive 1 charge. However, if we remember back to our section on weak acids, quaternary amines can function as Bronsted-Lowry acids. So technically, this guy can donate this hydrogen to a solution depending on the pH and some other factors that we'll discuss. So the quaternary amine can also be a tertiary amine with no net negative charge. Right? In the right solution, this guy will donate his hydrogen and will no longer be protonated. Similarly, over here, our carboxylic acid in the right environment can donate his hydrogen group, and now he can carry a negative 1 charge. So again, these characteristics are unique to each amino acid, but all the amino acids share very similar characteristics. So every amino acid is going to have a quaternary amine that can function as an acid base, and every amino acid will also have a carboxylic acid that can function as an acid or base, again, depending on the surrounding solution that it's in. And then beyond that, which isn't very spectacular on glycine, is that, remember, some amino acids have unique R groups, and some of these R groups contain ionizable functional groups or ionizable side chains. So while glycine only has 2 functional groups that can donate or accept hydrogens from the local solution, some amino acids have these R groups that can donate additional hydrogens. So if this is a little confusing, again, think back or remember to our discussion in class or outside of class about weak acids. So each of these functional groups can behave as its own unique weak acid. And remember, one of the main characteristics of weak acids are that when protonated, they can be represented generically as HA, and then when unprotonated, they dissociate into the conjugate base over here, A minus, as well as one H plus. And this happens in an incomplete fashion and at equilibrium. And that equilibrium is dependent on the surrounding solution, the pH, the contents of the surrounding solution, as well as the pH of the surrounding solution, right? So sometimes when conditions dictate it, our weak acids can dissociate more readily, or sometimes they will reassociate more readily, right? And so one unique characteristic, again, remembering back to how weak acids work, is that all weak acids tend to have the same shape to their titration curves. So over here we have an example from one of our textbooks of the titration curve for acetic acid. So here you can see as more equivalents of OH are added, we see a rapid rise in pH, and then a slow rise in pH, and then again another rapid rise in pH. Right? So as more and more sodium hydroxide is added to solution, more and more hydrogens can be pulled off of our acetic acid, or in other words, more and more dissociation of our acetic acid occurs. So this reaction moves to the right. And then unique to each weak acid is their capacity to buffer. So each weak acid has its own unique buffering region. Here for acetic acid, it's roughly 3.5 to 6.5. It's usually plus or minus 1 of its pKa. And at the center of this buffer region is what's referred to again as pKa. Remember our discussions from weak acids. So at when the pH of our solution equals our pKa, this dissociation reaction here is at equilibrium, and the concentration of A minus is equal to the concentration of HA, right? So there's just as much dissociated acidic ion as there is undissociated acidic ion. And that's one of the founding principles that makes weak acids really cool, and how well they function as buffers. So this is a single protonated acid, right? So we only have one pKa here, one buffer region or one flattening of our curve. However, not every weak acid only has one hydrogen it can donate to solution, right? Some weak acids, such as phosphoric acid, can have 2 or even 3 hydrogens they can donate to the solution around them. So in this case, if we observe the full titration curve of phosphoric acid, we'll notice that there are 3 flattenings of our titration curve. And each of these occur at a pKa for each of our hydrogens right here, right? So each hydrogen, phosphoric acid has 3, has its own unique pKa, which causes these flattenings of the curve. So we can pretend that, let's start with titrating H3PO4, so a fully protonated phosphoric acid. When our first hydrogen removes itself, now we're left with a hydrogen and an H2PO4. So that would be observed right here at this point in the titration curve. If we continue to add sodium hydroxide to our solution, we're going to continue to neutralize more and more acid, and eventually will cause our H2PO4 to also dissociate and donate hydrogens to the surrounding solution. And so that would be the flattening here. So the hydrogen here has a unique pKa, and the hydrogen here has a unique pKa, right? So think of this as the first hydrogen, the H3, and then think of this as the second hydrogen, H2. And then what I won't have animated in here is this last hydrogen, right? So under the right circumstances, he can also dissociate and be donated to the surrounding solution, and his pKa would be right up here. So, because of the unique properties of amino acids and the functional groups contained within them, we can observe something very similar if we were to titrate a amino acid completely, right? So, like I mentioned before, this is glycine up here. Glycine has one potentially acidic functional group here, a quaternary amine, and then under the right circumstances, this carboxylic acid would be would also contain a hydrogen and could function as a Bronsted-Lowry acid. So what does the titration curve of glycine look like? Here it is. So, as I mentioned, there's two acidic hydrogens in glycine, so we observe one flattening of the curve and two flattening of the curves. And again, remember, each flattening of the titration curve is relative to the pKa of the functional group that donates that acid to solution. So let's observe which flattening of the titration curve of glycine corresponds to which functional group, right? So again, here's glycine. It turns out that here, our first flattening of the curve corresponds to a pH of 2.34, right? And so we know that at a pH of 2.34, we've now reached the pKa of one of the functional groups up here that can donate an acidic proton to solution. It turns out that this pKa corresponds to the carboxylic acid over here on the right of our glycine. So at a pKa of 2.34, the dissociation of our carboxylic acid, COOH, is in equilibrium with H plus and the CO minus in solution, right? So there's as much conjugate base as there is Bronsted-Lowry acid in solution. Now, if we continue to the right on our titration curve, we'll notice that the next flattening of our curve occurs at a pH of 9.6. So this means a functional group within our amino acid has a pKa of 9.6. So we've already discussed the pKa of our carboxylic acid over here, which is much lower. Now we have reached the pKa of our quaternary mean. So quaternary means can dissociate and donate a hydrogen to solution, and then if this was attached to our amino acid up here, it would just be NH2. So here, at a pH of 9.6, our amine conjugate base is in equal concentration ratio to our quaternary amine, or our Bronsted-Lowry acid. So that is where the pKa's of our two functional groups stack up on our titration curves. So flattening here, right? So the take home here is that the titration curve of an amino acid very closely mimics the titration curve of a di- or triprotic weak acid. So we can use some of the same principles we discussed when discussing weak acids when we talk about the protonation state and ionization state of amino acids. So now that we've loosely discussed at which pHs certain functional groups in an amino acid will donate or accept hydrogens, let's take a slightly closer look, because it turns out that the ionization state of these functional groups can have large impacts of how we look at amino acids, how we isolate proteins, and then ultimately how individual amino acids can cause drastic changes in function of larger proteins. So one way to do this is to go step by step through our amino acid and our titration curve. So up here again we still have glycine. This is currently drawn as if it was placed in a pH of 7. So notice our carboxylic acid is dissociated. He's donated his hydrogen to solution, and our quaternary amine is still protonated, right? And so when we take a closer look, maybe this will make a little more sense as to why at a pH of 7 this guy is protonated and this guy is unprotonated. So let's start our observations by honing in on our functional groups. So here are two acidic functional groups. So now let's take a look at what our amino acid would look like at a pH of 1, right? So down here in the bottom left. At a pH of 1, we'll notice that we're far to the left of the pKa for our carboxylic acid, and we're far to the left of the pKa of our quaternary amine over here, right? So we know, remembering back to our discussion on weak acids, that if you're to the left of a pKa of an acid on a titration curve, that means that functional group is typically fully protonated. So at a pH of 1, both our carboxylic acid and our quaternary amine are protonated. So this can translate to ionization states in our amino acid or of our amino acids. So our carboxylic acid here is currently neutral, right? A COOH doesn't have a formal charge, but our quaternary amine over here still carries a formal positive 1 charge. So at a pH of 1, our amino acid has a net positive charge of 1. Next, how about we look at what our amino acid looks like at a pH of 5, right? So right here in between the pKa of both of our functional groups. So here, now we are far to the right of the pKa of our carboxylic acid, right? Far to the right. But we are still far to the left of the pKa of our quaternary amine. So structurally what this would mean is that now, since we are to the right of the weak acid, which is our carboxylic acid functional group here, our carboxylic acid has now become deprotonated. It can now readily donate that hydrogen to the surrounding solutions. So now, this means our carboxylic acid group carries a net charge of -1. But our quaternary amine still carries a net positive charge of +1. So, all in all, the net charge of our amino acid here is 0. And this is going to carry some implications in a couple slides when we start talking about Zwitter ions and isoelectric points. So let's test one more pH. Let's see what the structure of our amino acid looks like at a pH of 13, right over here. So now we are still far to the right of the pKa of our carboxylic acid functional group, and now we are to the right of the pKa of our quaternary amine. So this means that both of our functional groups will readily donate their acidic protons to the surrounding solution. So our carboxylic acid group doesn't change, it still has a -1 charge, but now we've lost that 1 hydrogen from our quaternary amine, and the charge on this functional group is 0. So if we plug this into our chart, we still have -1 for our carboxylic acid group because he's dissociated, but our quaternary amine now has a 0 charge because he's back down at NH2 with a side chain. And this results in a net negative charge of 1 for our whole amino acid, right? So if we look more closely, now that means that at a pH somewhere between 1 and 13, right, some pH somewhere between 1 and 13, our amino acid has a complete net charge of 0, right? So this 0 is technically just an estimate because we're not sure exactly where between 13 and 1 an absolute 0 charge is. So luckily for us, we have a way to determine this. And we can determine this by looking at pHs between the pKa of our quaternary amine, 9.6. So this is the functional group, basically the closest functional group with a pKa above the pH we tested for 0, and then the pKa of our carboxylic acid, which is the closest pH-pKa combination below the pH we tested where we received a 0. Right, so somewhere in between a pH of 9.6 and a pH of 2.34 is where true 0 will lie. Right, and so that's what we're looking at up here. Somewhere between this pKa and this pKa, there is a complete net 0 charge on our amino acid. So the unique name for an ion such as this, so our amino acid here has a net +1 charge or a formal +1 charge on our quaternary amine and a formal negative charge on our carboxylic acid. Molecules like this are referred to as Zwitter ions. So Zwitter ions are molecules that have a net 0 charge but both a negative and positive formal charge within its structure. And again, between a pH of 2.34 and a pH of 9.6 is the range that we have for our glycine amino acid, where it will be a Zwitter ion. Because above a pH of 9.6, our amino acid has a net negative charge, and then below a pH of 2.34, he has a net positive charge, right? If we go back to the previous slide, you can see this in our chart. So here are our ionizable functional groups. Again, pH, pKa combo, pH-pKa combo. So there's actually a unique name for the pH at which our amino acid or peptide has a complete net zero charge. This is referred to as the isoelectric point. So this is, again, where the pH where an amino acid, or on a larger scale, polypeptides and proteins, has a net zero charge. And so far, we've only really discussed an estimate of where this isoelectric point is. We're going to go through the next few steps to calculate exactly where the isoelectric point of this is. And so why this is important is because at the isoelectric point, so the pH where our molecule or peptide will carry no net charge, we can place our molecule of interest into an electrical field, and if it's at the correct pH, our molecule or amino acid or protein will not move, right? So if it has no net charge, it won't move towards the positive end of our electrical field or the negative end of our electrical field. And this is completely dictated by the functional groups in our polypeptides or our amino acids, right? So each unique functional group is going to have a unique pKa. So here we've only really discussed the pKa of this carboxylic acid group on this amino acid, again glycine, and the pKa of the quaternary amine on glycine, right? So the quaternary amine on other amino acids will not have the exact same pKa. So the isoelectric point for each amino acid and each peptide is technically different, which so requires going through this process to calculate or observe. All right, so let's look at this from a slightly more technical aspect, right? So we previously looked at the charges on our functional groups at different pHs. We've determined that somewhere between a pH of 9.6 and a pH of 2.34 is our isoelectric point. The way we calculate this, again, so somewhere between here and here, our molecule will have a total net zero charge. The way we calculate this is by simply taking the pKa that's on the low end of our pH of 0, right? So we tested a pH, we found the net charge on our amino acid to be 0. So we take the pKa below this and the pKa above this and simply take the average, which averages out to 5.97. And we've now found that the isoelectric point of glycine is at a pH of 5.97. So if we were to place glycine into an electrical field in a solution with a pH of 5.97, it wouldn't move towards the anode or the cathode. So for reference, I've placed our table here that we just walked through when we did our titration of our amino acid glycine. So now we're going to use this to figure out which direction our amino acid would travel at a given pH in an electrical field. So remember, our ionizable functional groups here are quaternary amine and our carboxylic acid. We know that at a pH of 1, the net charge on this amino acid will be positive 1. This guy is protonated with a 0 charge, and this guy is protonated with a positive 1 charge. So in an electrical field, at a pH of 1, our amino acid will travel towards the cathode. Remember, cation ions travel towards the cathode in electrical fields. How about at a pH of 13? So if we place our amino acid into a solution at a pH of 13, now our carboxylic acid and our quaternary amine are both deprotonated. So this will carry a net negative 1 charge, or a formal negative 1 charge. And our amine group over here will now carry a formal charge of 0. So the total net charge at a pH of 13 again is negative 1. If we place this into an electrical field, turn on the juice, our amino acid is going to travel towards the anode now. Remember, anions travel towards the anode in an electrical field. So at our isoelectric point, somewhere between pH of 13 and pH of 1, our quaternary amine will have a positive formal 1 charge, and our carboxylic acid will have a negative formal charge. So the overall net charge on our amino acid at the isoelectric point is 0. If we were to place our amino acid into a solution at a pH that matches our isoelectric point, our amino acid would not travel towards either the anode or the cathode. So more largely, why we care about these things, I previously mentioned that right now we're exploring the protonation state of different functional groups in different amino acids, because this will have a much larger impact on protein function, right? So this is one of the reasons proteins misfold or unfold or fold improperly at different pHs, right? And in the lab, we use things like isoelectric point to help us isolate certain proteins, right? So we can explore and isolate and precipitate specific proteins by placing them into solutions of different pHs and running them in an electrical field. So some proteins will carry a net negative charge, which will make them travel towards the anode, and then some proteins will carry a net positive charge, which will make them travel towards the cathode. And then some proteins still will carry that no formal charge, right? So in this case, this black protein here has been placed into a solution at a pH equivalent to its isoelectric point. So it won't move towards the anode or cathode, and in a lab we could use this to isolate it.